Ever wished you could, like, reshape reality?
Hmm.
Well, with matrices,
Yeah,
you kind of can.
that's right. Matrices are way more than just,
Right.
rows and columns of numbers.
Yeah.
They're like a secret language for manipulating space itself.
Okay, I'm intrigued, but how do numbers on a page
Right.
turn into, like, warping and twisting space?
So think about it this way.
Okay.
Each column of a matrix can represent a vector. And a vector is basically an arrow with a specific direction and length.
So instead of seeing a grid of numbers,
Yeah,
I should imagine a bunch of arrows.
exactly. And those arrows help define shapes and movements within a space.
Okay.
It's like each matrix holds a set of instructions for how to move,
Mhm.
stretch, or even flip objects within that space.
So it's not just about calculating stuff, it's about actually visualizing how things change.
Absolutely. One of the cool things is that matrices can create entirely new coordinate systems.
Oh, wow.
Instead of our usual X and Y axis, a matrix uses its column vectors as its own set of directions.
So it's like creating a whole new map
Yeah,
with different north, south, east, and west.
that's a great way to put it. It changes how we describe the location of every single point in space,
Wow.
like learning a whole new language for navigating.
Wow. I'm starting to see how powerful this could be.
Yeah.
But how do we actually use matrices to transform space?
Mhm.
Like, how do we take a shape and actually move it using a matrix?
So imagine a matrix as a set of instructions.
Okay.
When you multiply that matrix by a vector,
Mm-hmm.
you're essentially applying those instructions to a specific point in space.
So if I wanted to rotate something,
Yeah.
I'd use a specific matrix for that.
Yeah,
And if I wanted to stretch it, I'd use a different one.
you got it. It's like having a toolbox full of different transformations,
Uh-huh.
and matrices are the keys to unlocking them.
This is blowing my mind a little.
Yeah,
Are there any tools within matrices that help us understand
Yeah.
what kind of transformation we're doing?
yeah. There are. One of the most useful is something called the determinant.
Okay.
It's a single number
Mm-hmm.
calculated from the matrix,
Okay.
and it tells you how much a matrix will scale areas or volumes.
So a bigger determinant means a bigger change in size.
Essentially, it acts like a magnification factor.
Okay. Yeah.
And here's something else. The sign of the determinant, whether it's positive or negative,
Okay.
tells you if the shape is flipped or mirrored during the transformation.
Okay, so the determinant tells us how much something changes size and whether it gets flipped.
Right.
What else can we learn from these matrix marvels?
Well, there are also these special vectors called eigenvectors.
Okay.
They're kind of like the unchangeables.
Mhm.
Even after a transformation, they point in the same direction,
Mm.
though their length might change.
So they're like the stubborn arrows that refuse to turn around.
Exactly. And each eigenvector has an eigenvalue,
Okay.
which tells you how much it gets stretched or shrunk during the transformation. It's like each eigenvector has its own personal growth spurt
Yeah.
while still pointing the same way.
So we've got these vectors that can stretch and squish,
Yeah.
matrices telling them what to do,
Mm-hmm.
and this determinate thing that tells us how much it all changes.
Right. And by understanding those pieces,
Yeah.
we can start to see how matrices let us manipulate and reshape space in all sorts of ways.
Yeah.
Yeah.
Wow.
It's pretty amazing.
That's incredible. So before we were talking about eigenvectors as these unchangeable vectors.
Right.
It seems like they play a pretty important role in all of this.
They do. Eigenvectors and their corresponding eigenvalues are essential for understanding the effects of a matrix transformation. They tell us which directions in the space are most affected by the transformation and by how much.
Okay, so if I imagine a matrix stretching and squishing space,
Yeah.
the eigenvectors would be like the lines along which the stretching or squishing is happening.
That's a great way to visualize it. The eigenvectors are the directions that remain essentially the same,
Right.
though they might be scaled up or down by their eigenvalues.
And the eigenvalues tell us the degree of that scaling.
Uh-huh.
So a large eigenvalue means a lot of stretching or shrinking along that particular eigenvector.
Precisely. And if an eigenvalue is negative,
Okay.
it means that the corresponding eigenvector is flipped in direction as well as scaled.
So the combination of eigenvectors and eigenvalues gives us a really detailed picture of how space is being transformed by a matrix.
Exactly. It's like they provide the blueprint for the transformation,
Right.
highlighting the most significant changes in the space.
This is all starting to make sense now,
Good.
but we've mainly talked about stretching and squishing.
Right.
Can matrices also handle rotations?
Of course, rotations are another fundamental transformation that can be represented by matrices.
Okay.
They're used extensively in computer graphics, physics, and engineering.
So how do we represent rotations with matrices? Is there a special kind of matrix for that?
There is. They're called rotation matrices.
Okay.
And they have a specific structure that ensures vectors are rotated around the origin without changing their length.
So a rotation matrix would essentially spin a vector around, like a hand on a clock,
Yeah,
keeping it the same distance from the center.
that's a great analogy.
Okay, cool.
And we can control the direction and angle of rotation by adjusting the values within the rotation matrix.
This is fascinating.
Yeah, it is.
So we have matrices that can scale, flip, and rotate space. What other tricks do they have up their sleeves? It's amazing how much we can do with matrices just by, manipulating those numbers.
Yeah.
But how does this all translate to the real world? Where do we actually see matrices in action?
Matrices are everywhere. They're the hidden engines behind so many technologies and scientific advancements.
Can you give me some examples? Like, how are matrices used in fields like computer science
Yes.
or engineering?
So think about computer graphics and animation.
Okay.
Every time you see a character move on a screen or an object rotate in a video game, chances are matrices are involved.
Oh, wow.
They're used to create those smooth transformations and movements.
So the movements of those characters are basically dictated by matrix multiplications happening behind the scenes.
Exactly. And it's not just about movement.
Right.
Matrices are also used in image processing.
Okay.
Like when you adjust the brightness or contrast of a photo,
Mm-hmm.
and they play a crucial role in machine learning algorithms, helping computers learn from data.
I had no idea they were so versatile.
Yeah,
Seems like matrices have a hand in almost every aspect of technology.
they do, and they're not limited to computer science
Oh,
and
sure.
engineering.
Yeah.
Matrices are essential for modeling and analyzing physical systems.
Okay.
They're used to calculate stresses and strains on structures, simulate fluid dynamics,
Wow.
and even predict the behavior of electrical circuits.
So they help engineers design things like bridges, airplanes, and even microchips.
Yes,
Yeah.
and they're used extensively in physics and other scientific fields to model complex phenomena and solve intricate equations.
It's incredible to think that these simple grids of numbers hold the key to understanding so much about the world around us.
That's the beauty of mathematics.
Yeah.
It provides a powerful language for describing and understanding patterns, relationships, and transformations,
Right.
both in the natural world and in our technological creations.
I think our listeners will never look at a matrix the same way again.
Yeah.
Who knew those rows and columns could hold so much power and potential?
It's a testament to the elegance and universality of mathematical concepts. And as we continue to explore and push the boundaries of mathematics, who knows what other amazing applications we might discover?
It's definitely something to ponder.
For sure.
So until next time, keep those mathematical minds curious. And remember, sometimes the most profound truths are hidden in plain sight, just waiting to be decoded.